So now we move on to Chapter 10, something involving heat. We're going to look at thermal physics and try to define how we look at heat in solids and fluids. So we're going to first look at how we define temperature and the Zeroth Law of thermodynamics, and then thermometers and temperature scales, thermal expansion of solids and fluids, how they react to heat and cold, a macroscopic description of something we call the ideal gas and using the ideal gas law and Avogadro's number, and then the kinetic theory of gases. So in the first portion here, let's look at something called the Zeroth Law of thermodynamics, or the law of equilibrium. Now we're talking about equilibrium as it relates to hot and cold. To understand the concept of temperature, it's useful to define thermal contact and thermal equilibrium. As we're discussing this, think about the last time you sat down in a chair in a classroom and the chair was cold, and it took a while for the chair to warm up, basically putting you both in equilibrium. Thermal contact, then, when two objects interact with each other to exchange heat between them. And we talk about this in engineering terms as heat transfer. Thermal equilibrium then says when two objects in thermal contact with each other cease to exchange energy. Okay, then they are at the same temperature. So again, think about that time you sat in that cold chair and you warmed it up. If objects A and B in this diagram then are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. We need to look at thermometers. How do we define the scale on a mercury thermometer? Well, you can see here we've got in Celsius or centigrade, one measuring the ice point and one measuring the steam point. Because of thermal expansion, the level of mercury rises as the temperature of the mercury changes from 0 Celsius, the ice point, to 100 degrees Celsius, the steam point. We can measure this accurately using something called a constant volume gas thermometer, and later we will define the Kelvin scale. A constant volume gas thermometer measures the pressure of gas contained in the flask immersed in a bath. So it's a measure of pressure as we change the temperature, which causes really a hydraulic effect with this column of mercury. The volume of gas in the flask is kept constant by raising or lowering the reservoir B, okay, the mercury reservoir, to keep the mercury level constant. If we look at a graphical depiction of what's going on, we pick our 2 points, 0 for the freezing point, 100 for the steam point, and we have a trend or a linear representation here in degrees Celsius. A typical graph of pressure versus temperature then, notice we have pressure on the vertical axis, temperature in Celsius on the vertical axis. This is taken with a constant volume gas thermometer. The dots represent then the known reference temperatures, the ice point and the steam point. So if we look at this by running trials of dilute gases, again, we can see the temperature and pressure relationship here. And notice that we have on the horizontal scale measured in Celsius minus 273.15. That's going to become an important number when we talk about Kelvin. So by definition, we can see from that graph that the temperature Celsius is equal to the difference in the temperature minus that point, minus 273.15. If we look at then a representation here of different temperatures for various selected physical processes, you'll notice temperature is in Kelvin, not degrees Kelvin, but Kelvin. And you can see 10 to the 8th, 10 to the 7th, 10 to the 6th, 10 to the 4th and 3rd and 4th, 10 squared, 10, and 1. Okay, 10 to the 0 power. Again, this is a logarithmic scale and not a linear scale. Please refer to the descriptions in your text to understand what's going on with this particular diagram. What becomes important then, especially in physics, is understanding how do we relate the Celsius, the Fahrenheit, and the Kelvin scale with each other. To do this, as we set them side by side, you can see that where the red line ends is common in each one of those. It's the same value. But the scale is different. On Celsius, we have 0 for the ice point, 100 for the steam point. On Fahrenheit, we have 32 degrees and 212. And in Kelvin, we have that 273.15 and 100 above it, which exactly matches the Celsius, 373.15. So you have to make sure you understand what scale you're in when you are doing your calculations and your analysis. Sometimes you need to convert from Fahrenheit to Celsius to Kelvin. Okay, there are some ways to do that easier. The most common temperature scale in use here in the United States is the Fahrenheit. Some of you may be more used to using the Celsius scale. Fahrenheit sets the temperature of the ice point at 32 degrees Fahrenheit and the temperature of the steam point at 212. The relationship then between Celsius and Fahrenheit is as noted here. Temperature in Fahrenheit is equal to 9/5 of the value in centigrade, and we add 32. Conversely, if we move our terms around, let's get temperature in Celsius to the other side, so we move Fahrenheit and Celsius to either side of the equation and solve for temperature in Celsius. Now we have 5/9 of the difference between Fahrenheit and 32. So this gives us then a change of temperature in Fahrenheit is equal to 9/5 of the change in centigrade. Sometimes we need to know the change rather than the absolute value. So the relationship then between Celsius and Kelvin is a little easier because that 273 point that we saw in the previous graph relates exactly to the freezing point, the ice point. And it has the same change of 100 in its scale. So it goes from 273.15 to 373.15. Let's look at an example. Heating a pan of water. We have a pan of water and it's heated from 25 degrees Celsius to 80 degrees Celsius. What is the change in its temperature on the Kelvin scale and on the Fahrenheit scale? So they want us to use those conversions. So the change is temperature on the Celsius scale equals the change on the Kelvin scale. That should be in temperature. So the change in temperature is equal to the change in temperature Celsius that we saw before, which is equal to the temperature final minus the temperature initial. In this case, it was given to us 80 degrees final, 25 degrees initial, gives us 55 degrees Celsius, which exactly equates to 55 degrees Kelvin. So now to change the change in temperature on the Fahrenheit scale is 9/5 as great as the change of the Celsius. So we need to use that conversion formula. So the change in temperature Fahrenheit is equal to 9/5 of the change in temperature. So we're not talking about absolute, we're talking about the change. So in this case, 80 minus 25, the difference in those two times 9/5 gives us a change in temperature of 99 degrees Fahrenheit. So the next thing we're going to look at is how does heat react and change solids and fluids physically, so we can have an understanding of what happens in nature when things start occurring, when things get too hot or too cold.